Right. Well, it's becoming more and more reminiscent of my undergraduate lectures. So my name is Paul Christensen, Newcastle University. I need to mention my funders, which is the Faraday Institution, who are essentially responsible for battery research in the UK. So this is the kind of thing I'm doing. I'm a senior advisor to the National Fire Chiefs Council, and I'm on various groups. I've been working with fire and rescue services for about 3 years now in the UK, Australia and New Zealand. And as it says at the bottom, I'm really cheap. So if you need help, you know where to come. Okay, so first question, what's a lithium-ion battery? It's the simplest battery you can get. So if you look at the top, it's essentially a very thin metal current collector, aluminium in one case, copper on the other side. Coated on the aluminium is a thin layer of a mixed metal oxide ink, okay, very thin. On the other side, it's a thin layer of soot, basically, graphite particles. And these are pressed either side of a very thin and fairly fragile plastic separator that's got holes in it, and it's soaked in a mixture of organic solvents, called carbonates, and lithium hexafluorophosphate. There are also up to about 5% additives in there, which we don't know because they're commercial secrets, but a number of them are toxic. So it's not a good idea to get yourself in contact with the electrolyte. So what happens? Well, when the battery is fully discharged, the lithium ions are in the mixed metal oxide inside the crystal structure. When you charge it, they move out of what's called the cathode, the mixed metal oxide, move through the solvent and go into the crystal structure of the graphite particles. And the reverse is when they discharge, and that's it. That literally is it. As such, there are no actual chemical changes. It's just insertion and deinsertion. It's so simple, it's called a rocking chair battery. Now, most, by far, lithium batteries now have graphite anodes. So we know the batteries by what the cathode is. So lithium cobalt oxide is LCO. Lithium nickel manganese cobalt oxide is NMC. Lithium iron phosphate is LFP, for ferrous rather than iron. And as you can see, you've got LCA, etc. So that's how we name the batteries. Now, the smallest unit of a battery is the cell. Many cells make a module or a string. Many strings or modules make a battery. And there are 3 primary form factors or shapes and sizes of lithium-ion cells. The cylindrical, which is typically a bit bigger than a AA cell. Prismatic, which is about the size of a couple of fag packets. And a pouch cell, which is about the size of an A4 sheet of paper and about 1 centimetre thick. Prismatic and cylindrical cells are spiral wound, essentially. The electrodes, both anode and cathode, either side of the separator, are very thin and they're wound into a spiral. So this is a typical Nissan Leaf battery. It has 192 cells in 24 modules, in other words, 8 cells per module. And a Tesla has over 7,000 cylindrical cells in a battery pack. And the first thing to note from an RTC point of view is that even if a pack is at 0 charge, it's still got 2.5 volts per cell. So fully charged would be typically 4.2 volts, and empty, inverted commas, will be 2.5 volts. So you've still got electric shock stroke electrocution hazard. So what makes lithium-ion batteries so special? They store a huge amount of energy in a very small space. It's the very first time we've had a battery like this, so energetic. It's streets ahead of anything else. No previous batteries come even close. So what makes lithium batteries not so special? They store a huge amount of energy in a very small space. And if that energy gets out in an uncontrolled fashion, then you can have fire or even explosion. Now, I'm not demonizing lithium-ion batteries. I think they're great, honestly. And I would have a Nissan Leaf. I'm prejudiced because I worked with Nissan. I would have a Nissan Leaf tomorrow if I was paid enough, which I'm not. So they're the first battery to use organic solvents rather than water. Now that makes them special for a start, because of course organic solvents are flammable and potentially explosive. They've also got lightweight plastic components which can burn. And the key point which makes them different from other batteries is that if you abuse them by overheating, by crushing them, by penetrating them, or by overcharging them, then they can actually burn or even explode, okay? And this is because of something called thermal runaway, which I'll deal with in a second. Now, when they go into thermal runaway, they generate a range of toxic and flammable gases. Now, there's a common fallacy that they can burn inside the cell because oxygen is also produced. That's nonsense. Nothing happens until they vent into the outside atmosphere. Now, the problem with these big batteries, like electric vehicle batteries, is that the fires burn for much longer. They require huge volumes of water, and even then, if the battery pack is intact, you can't put the fire out. You can't access the battery. And they can reignite hours, days, or even weeks after the initial incident, and it can take place many times. And of course, you've got stranded electrical energy, and that can give you the risk of electric shock or even electrocution, and of arc flash explosion, which is very nasty as well. So the problem comes with the fact that when they're abused, they go into thermal runaway. And in simple terms, when the battery is operating normally, when it's an electrochemical device, if you stop the electrons from flowing in the external circuit, break the circuit, or you stop the ions from flowing inside the cell, you will stop anything happening. But when they're abused, they start undergoing chemical processes which supersede the electrochemical processes. These chemical processes generate heat and gases. Now, heat speeds up chemical processes in an exponential fashion, the red line. So you're generating more heat and more gases, and then more heat, and you're in a self-fulfilling loop, okay? Now, heat is produced in a dissipated in a linear fashion, as you can see. And it is also dissipated over the surface area of the object. But heat is produced by chemical processes exponentially, as I've just said, and throughout the volume of whatever you've got. Now, once those two lines cross, then you have a self-perpetuating process. And there's an argument about when does thermal runaway start. Sometimes you'll see it down as 1 degree centigrade rise per second, or 10 degrees centigrade per minute. That's because you can measure them. A more accurate description is when those exothermic heat-producing processes become self-sustaining, okay? Once it's in thermal runaway, you get a whole range of gases. Note, hydrogen, 30 to 50%, carbon monoxide, both flammable, carbon dioxide, hydrogen fluoride, extremely nasty, hydrogen cyanide, extremely nasty, hydrogen chloride's not very pleasant either. You get small droplets of organic solvents, you get small organic molecules like ethene, methane, and other hydrocarbons, and you get SO2 and NO2. In rough terms, it doesn't matter what the battery is, that's what you'll get. The amounts might differ, the ratios might differ, but that's what you get. Once those vent from the cell, they take with them the small droplets of organic solvent. And that gives it its white colour. It's a vapour cloud. And I don't need to remind you guys of Buncefield, yeah? Vapour cloud explosion. Now, thermal runaway should be prevented by the number of safety systems that you have even in your mobile phone battery. It has safety systems. You've got a battery management system, you've got chemical systems inside those additives, all of which are designed to stop thermal runaway. But the trouble is, most of them rely on breaking the circuit, the electrical circuit or the ionic circuit. And by the time it's in thermal runaway, that's irrelevant, okay? Chemical processes have taken over. So this typifies the kind of problems that you face. Now, in fact, this was a Tesla X SUV that crashed on Freeway 101 in Mountain View. The fire service in Mountain View are the luckiest when it comes to electric vehicles because that's where Tesla's based, and they have a hotline to Tesla. They were also lucky because the battery pack was ripped open, so they could actually access the cells and put them out. Sadly, the driver was killed in this crash. As you can see, it was pretty horrendous. The battery pack was ripped open, and about 25% of the cells were spread across the 6 lanes of the freeway, which was shut for about 6 hours. And that's another common factor. Because of the special nature of the challenge of electric vehicles, the roads need to be closed for a lot longer, and it can be days, never mind hours. So the Tesla experts came along, and basically they picked up all the scattered cells and dropped them into buckets of water. They carted away what remained of the car, which still had 75% of the battery pack, which, as you can see, ignited twice in the next 24 hours, then again 6 days later. Now, in Netherlands and in Germany, I believe, they tend to drop EVs that have been in an RTC into a sea container full of water. The Americans don't have quite that kind of funding, so what they tend to do is to take it to a scrapyard, build a dam around it and fill the dam with water, and then just leave it. They also establish perimeters around these vehicles, okay, exclusion zones. And there's been a number of electric vehicle fires, including spontaneous ones. Now, we're not quite sure why these happen, but we suspect that it's due to defects or contamination introduced during manufacture that then takes a long time to show up and to cause a problem. This one burst into flames just after being charged, and this does happen. Charging does seem to be like an additional risk factor, enhance the risk or the probability. Took 45 minutes to extinguish that blaze. Now, this is a video, it's available, it's the Sun newspaper. If you just search Moscow freeway, Tesla crash. The Tesla crashed and then skidded into the side. And this represents the different challenge that you face. Remember, there's no diesel and there's no petrol. So there's no diesel and there's no petrol. That exploded twice, and those white incandescent things you could see was molten aluminium being projected. You will be maybe told that as firefighters, you're used to dealing with toxic gas. You're used to dealing with stranded electrical energy. You're used to dealing with fire and flammable gases and potential explosions. But these are all together, and it's a pick and mix. And that's what makes this different. It's a pick and mix. You can have one, you can have all of them, or you can have a selection. This is a garage again in Shanghai. Electric vehicle spontaneously combusts, takes out the vehicles either side. And it's interesting that the public are not allowed to fill an internal combustion engine with diesel or petrol. But car parks, multi-storey enclosed car parks, are being built with chargers, and car parks underground beneath flats are being built with chargers. And think about that. Now, you will also be told that the heat release rate for an electric vehicle is about the same as for an internal combustion engine. Yeah, okay. But internal combustion engine cars, when they tend to burn, it's not directional. You're not focusing that heat. And this is a video of a van, electric van in China being charged, and it includes several interesting points that I want to bring out. First thing is that you get the emission of cathode particles, those heavy metals, cobalt, manganese, nickel. Those are just dust particles. You can just hear a slight whistle. That's the gases coming out like a rocket flame. The flames are highly directional, so you could be focusing those flames directly on the car next door. Now watch the wing mirror of the lorry next door. Those flames are not really touching it. It just melts away. So you've got highly directional flames, very high temperature flames, okay? Initially you get the emission of black particles, and then what you actually got was the vapor cloud, that white vapor cloud. Don't mistake it for smoke. The danger isn't over, right? The danger of explosion isn't over if you see that. It's there. And don't mistake it for steam, because when you put water onto an electric vehicle, the fire will go out, but the white vapor will still be produced because the cells will still be in thermal runaway and sending others into thermal runaway. And this shows you the fire service, right? They know that there's an electric vehicle in thermal runaway, so they're cooling it. It ignites and then it explodes and it rips a hole in that metal roof. Explosion risk from an electric vehicle is real. And what I'm going to say and repeat is that vapor cloud explosions are not confined to big battery installations, the big sea containers with batteries. You can get them anywhere, potentially. And we've seen them on boats, we've seen them in battery energy storage systems, we've seen them with cars. And you will see, we've also seen them in another context with a car. Again, this highlights the kind of problems you might face. Electric vehicle crash, put the fire out. About 45 minutes later, it starts to emit what they think is smoke. So they don't believe that there's an explosion risk, it's smoke or steam. Then you get the jet-like flames, okay? It takes 90 minutes of high-flow water. Luckily, there was a stream nearby. They put it out, and it takes a lot of water. And then after about an hour, they load it onto a tow truck. There was probably a spark, because the battery's still energized, and up it went again. And electric vehicles have reignited hours, days, or even weeks after the initial incident. And this shows you another, and this is really very important, and I only realized this when I was watching this a couple of minutes ago before this lecture. Watch this video. It's some electric buses in China. Notice the white, now that is critical. You get white vapor, and then I don't know if you noticed, but it actually exploded, and the vapor was consumed. When the vapor ignites, it's replaced by a thin fume. That vapor actually deflagrated. And although it talks about thick smoke, it's not thick smoke. That's the vapor cloud that then explodes. So it's not just, or rather, you could face a vapor cloud explosion as well as fire and toxic gas under a number of different circumstances. This is kind of a summary of electric vehicle instances, including the great number of recalls of the Chevy Bolt and the Hyundai Kona, both of which got 5-star NHTSA safety ratings, by the way. Recalls, fires are happening almost on a daily basis. And bear in mind, they're still tiny compared to the number of vehicles on the road, okay? But a Freedom of Information request from friends of mine in Australia to the London Fire Brigade brought back very raw statistics, but those statistics suggest that the likelihood of fire is about 2.5 times for an electric vehicle compared to an internal combustion. Very raw statistics, though. This is the most recent announcement from GM, telling Bolt owners to park 50 feet from other cars in parking garages, right? Now, this is important because it shows that even the most experienced, knowledgeable, careful manufacturers are still getting defective cells passing through their very careful quality control systems, okay? Now, I know you guys can put out a fire and open a road again in an hour if it's a conventional electric vehicle. You got no chance with conventional internal combustion vehicle. You got no chance with an electric vehicle. You're looking at much, much longer because of the danger of reignition, because of problems of gas, etc. And what about an electric vehicle fire on a busy junction like the M25? And also, of course, recovery services are becoming a bit leery about dealing with RTCs involving electric vehicles because of the danger of reignition. And a couple of tips that come from my contacts in Australia who've got quite a lot of experience of this. Beware of remote operation keys. You don't need to be near the car to start it up. They are trialling a hot stick to detect DC, stranded electrical energy. Up till now, you've only been able to detect AC, but they're trialling a hot stick. Avoid towing, because of course that will activate the motor, which will generate electricity. And be wary of contact with battery fluids. In fact, seek first aid instantly. Perhaps an unexpected hazard, you've got the mobile energy or electricity supply. These are 60 kilowatt hour vans with 60 kilowatt hour battery energy storage systems in the back, so that if your shop or house goes down, they come up, hook into your mains. There's no signage indicating that's an electric vehicle or that it's got a battery energy storage system on board. There's no real ventilation to cool the cells. Bear in mind, in general, that lithium-ion batteries start to go unstable at about 60 degrees centigrade. Okay, so let's concentrate on what happens. So you get thermal runaway. This generates the gases inside the cell. At some point, the gases vent, either because the cell bursts, if it's a pouch cell, or the blast cap goes, if it's a prismatic or cylindrical cell. If that gas ignites immediately, then in many ways that's good news. You get flare-like flames and you get a thin fume. Once you're just left with the plastics, you get a thick, smoky fume. But, okay, and also you get, usually at the beginning, you get the ejection of those toxic particles from the cathode, the manganese, the nickel, the cobalt, the heavy metals, in other words. If ignition is delayed, then you've got the fact it's a toxic cloud, but also it's a vapor cloud, and you've got the possibility of vapor cloud explosion. So these are some experiments I did at RAF Spade Adam, just north of here, up in the wilds of Northumberland. And forget the way I'm abusing these cells. Doesn't matter. What you will see can happen whether they're crushed, heated, or nail penetrated, or overcharged, okay? So we did our experiments either outside or inside a 40-foot container. And what I'm going to show are mainly modules, which are 1.7 kilowatt hours, okay? There's 24 modules in an electric vehicle. There's 8 cells in a module. And I have to greatly thank Envision AESC, the manufacturer, because they've been really supportive of this work with the fire service, really very supportive. And the methods I'm using are pretty violent, okay, just to make sure that things happened. But it doesn't matter. The way that you would see this from thermal, from overcharge, whatever. So the first one is just to show you what happens when it ignites immediately. Now, what I want you also to take note is that that hammer is actually 23 kilograms, and there's a nail hanging off it. And that's going to penetrate all 8 cells, okay? But that's a 23 kilogram hammer. So you saw how high that jumped. And that's, the can that it's in is not very strong. It's just got little tabs holding the 2 sides together. And that threw the hammer. And you can see those flames are highly directional. Yeah? And of course, at the beginning, you will have seen the black heavy metal powders ejected. Now, the next one is, this is a mock-up of a battery energy storage system. Typical domestic battery energy storage systems in the home are between 2 and 130 kilowatt hours, the ones you can buy. So one of those modules is about 1.7 kilowatt hours, and we've got 8 of them, okay? We're just going to overcharge 2 cells out of the 8 cells in that far left-hand module. Now, this isn't about domestic systems. This is still about electric vehicles, and you'll see why in a second. So we're only overcharging 2 cells, remember, and there's 64 in total. And that's not speeded up. Now listen, you can hear the crackling. And that's still just 2 cells. What you can't see is that the flames out the back are hitting the wall. Now that crackling noise kind of confused us for a bit, and then we looked at the drone video. And I have to say, I've never had so much fun in all my life as during these experiments, right? So If you look, you can see there's lumps of the concrete are being projected, actually 20 metres in some cases, and 10 metres vertically. What's happening is that the flames are so hot, so directional, they are actually causing the water inside the concrete to explosively expand, and chunks of concrete are being thrown out. Now, in Germany, a number of cities started banning electric vehicles from parking houses, as they called them, the enclosed parking houses. And in fact, it seems to have spread across the whole country now. And there are worries that this will affect the sale of electric vehicles. But the reason they're worried about this is that they know that electric vehicle fires can only be controlled. They can't be extinguished, essentially. So they're now worried about structural damage. And I think this video kind of highlights that point. Now, if the gases don't ignite, then you get the vapour cloud forming. And again, this is nail penetration, and we're doing this at 40% charge, in other words, just under half charge, because we know that the vapour cloud doesn't ignite in that way. And again, it doesn't matter. You can have it on full charge, it can be overcharged, whatever. If for any reason there isn't enough oxygen, or if it's at low charge, the vapour cloud won't ignite. If there's not enough oxygen, the mixture is too rich, obviously. So this shows you what happens. Oops, back. If you don't get immediate ignition. So you'll see the black powder blasted out first. And then you're getting the vapour cloud. Now, it turns out we don't know why. There are two types of vapour cloud. There's a buoyant vapour cloud that fills the room from the top down, and then there's a heavier than air vapour cloud that fills the room from the ground up. Okay? So we don't know, and you tend to get both, but one predominates. So we've seen this container fill from the ground up for one kind of battery, and from the top down for a second kind of battery. So you can see the second type of vapour cloud starts to form in a second or two. And we had full sensors and everything monitoring this, gas sensors, HF sensors, hydrogen sensors. Now you can start seeing the heavier than air vapour cloud. And we know for sure that the Surprise explosion, the McMicken battery energy storage system that exploded in Surprise in 2019, was a vapour cloud explosion. And people saw the vapour cloud, which was a heavier than air vapour cloud. Okay? When the module ignites, those clouds all reverse because they're consumed by the fire. Now, as I said, vapour cloud explosions are not confined to big battery energy storage systems. This is an experiment that CSIRO did because a lot of Australian homes, because they get a lot more sunshine than we do, surprisingly, have battery energy storage systems in the garage, lithium batteries. And CSIRO were a bit worried about somebody reversing into one of these. So they set up this experiment with you can see the tow bar on a pneumatic system, mocking up a kind of garage. And they set the tow bar against the battery energy storage system at about 10 kilometers a second. Oops. Oh, I've lost my cursor. There we are. So initially you get the black powder, then you get the vapour cloud. And there's little ignition source just will show through. Now watch what happens. Bang. And that was wholly unexpected. And that research has been shut down. It damaged the container, blew one of the sides off. It was a vapour cloud explosion. Now, I have to thank David Smythe of Vehicle Fire Blanket for this. It's testing his fire blanket, and I do believe fire blankets have a role to play. But the bottom message, or the most important message of this presentation is that you guys must understand what you're dealing with, okay? Now, luckily, there was a very high wind blowing when this was done. It was a test done at Hariba Myra, and They set an electric vehicle alight, overcharged it, it burst into flames, the batteries burned, and then they put a blanket over it and it completely smothered the air, okay? And it stopped the fire. But that's temporary. As soon as you take the blanket off, it will reignite. But in the meantime, it's boiling off that white vapor. The firefighters clearly believed that that white vapor was smoke. They didn't realize that apart from being toxic, it was potentially explosive as well. Again, I've got to find my, I'll just press my cursor. You can see the white vapor that's coming off. And when they lift the cover off, there's no flames at all. The cells are in thermal runaway and they're generating the white vapor. And look how much there is. And remember what that's comprised. And that's what you could face in an underground environment. You'd have to be smoke diving to deal with this. Now watch the guy on the right. Quite rightly, they're all wearing full breathing apparatus, etc. Watch what happens when he pulls the blanket slightly away. And luckily for him, there was a very high wind. That was a small vapor cloud explosion. There's no petrol in there, there's no diesel. Okay? And this is a high-end corner, and it's in thermal runaway. These firefighters believe that's smoke, and the actual caption said smoke. And they've allowed people to watch. You can see just behind the fence. It's an enclosed space. Okay? You've already seen that a vehicle can be an enclosed space, sufficiently enclosed to allow a vapor cloud explosion. So I want you to think of something. You've got an extrication. The electric vehicle's crashed, the driver's trapped. You start to try and get him out, and you hear a hissing. That's the first indication that the cells are in thermal runaway and they're venting. And then you see white vapor, thick white vapor billowing out. What do you do next? And this is a heads up. You could face a vapor cloud explosion as well as fire or toxic fumes under a whole range of situations. Not just electric vehicle road traffic collisions, but in warehouses, manufacturing plants, in the home, in a house, okay? As well as in industrial battery energy storage systems. And we've already had one on Merseyside in September last year. Or should I say we've had our first one. Be aware, be prepared. And I have to say that apart from domestic battery energy storage systems, my nightmare scenario is an RTC with a trapped person. Now, I've heard use water lancers, but I'm not sure having one of you guys pressed against the car with a water lance is a good idea. Just like I don't think it's a good idea pressed against a sea container for a battery energy storage system. I don't know. I'm not an expert. You are the experts. But for goodness sake, be aware. Now, NFPA field guide is good, really good, and it's free, how to treat electric vehicle fires. And we are testing so-called lithium battery specialised fire extinguishers, hoping to do it at Manchester Airport. Unfortunately, they've suffered from the pandemic, etc., so their manpower has been somewhat reduced, so we've had to defer it probably until October, but we're hoping to do a water lance, encapsulating agents, AVD, things like that. And is this the next phase? This is an electric vehicle, it's a Leaf, and I'm not aware of any Leaf instances prior to this. A couple of days ago, it must only have been 3 years old or less, and it was being transported from Germany to the Ukraine through Poland, and it spontaneously went up. Now, my second in command is Polish and rang up the local fire chief to ask about this, and the first indications, although it's not for sure, is that there was water got into the battery pack. Now, that's nothing to do with the battery pack itself. That's normal wear and tear, okay? So second-hand electric vehicles are coming onto the market. In fact, they've been on the market for a while. You're going to start seeing backstreet garages, third-party garages fixing them. And how much do they know about the risks and hazards? And thanks that you didn't fall asleep. Thank you for your kind attention.